Hi, this is Professor Fernandez. We are working on class notes A in lesson 7. And this example that is up here asks us to show that first a certain set of functions are not independent functions, and then a certain set of functions are independent functions. So again, let me scroll up and see where this comes from and why it's useful. So there's a lot that happened before this example, but I'm just going to focus here on the main theorem that we are going to be doing this for. This is theorem 7.1.2. The theorem says, let y1 through yn be n independent solutions of a homogeneous nth order linear ODE. And it tells us what independent solution means. So this is the key definition. No solution y sub j is a linear combination of the other solutions. Then every solution y of t of that homogeneous nth order linear ODE is of the form this. So, you should recognize this as a generalization of what we've been doing in this course for second order linear ODEs. Usually for second order linear ODEs, the general solution looks like this, provided that y1 and y2 are fundamental sets of solutions. And all the other requirements of that theorem in lesson 3 or 4, I believe, are satisfied. It must be somewhere around lesson 3 or 4. So this theorem is a generalization of this result for the nth order linear ODE case. But like I say down here, back in the second order linear ODE case, we used to use the Wronskian to tell us whether y1 and y2 were, quote, independent solutions. We didn't use that terminology back then because we had the Wronskian. So we use the terminology of fundamental sets of solutions for these two. But in this setting, the Wronskian is this determinant of this n by n matrix. And thus far in the course, we're in lesson 7. We haven't talked about matrices. We haven't talked about determinants. So I did not want to do that yet. So this is what will turn out, excuse me, as I say here, to be an equivalent way of analyzing, of getting to the same general solution conclusion, which is to require that no solution is a linear combination of the other ones. Okay, so that's why we care about this property of no solution is a linear combination of the other ones. That makes the solutions independent. And along with the other assumptions here, a homogeneous solid, that gets us this general structure of the solution, general solution to a homogeneous node, which is what we're after in general. So let's go down here back to the example and talk about how you determine, show you an example, illustrate how you determine that a set of functions is independent or not. So I've typed out some of the work here so I can talk through it a little faster and easier. So for the first one, we're looking at these three sets of functions. And we want to show that they are not independent functions. In other words, by the definition we just chatted about, we want to show that no function here is a linear combination of the others. Now, when we talk about linear algebra in a few lessons, we will have a very algorithmic and detailed way to do this. But at this point in the course, we don't have that, so we're going to try our best to do without it. So what am I going to say? I'm going to say let y1 be the first function, y2 the second, and y3 the third. And then now our job in this particular example, because they're telling us they are not independent functions, right? Our job is to find a relationship between these three functions that is of the form, one function equals linear combination of the other two. And I have chosen the example to make it a little easier for us to see that. We can certainly see that 2e to the t is related to e to the t, right? The only difference here is that this one has a factor of 2. So that's what I've written here. y3, which is 2e to the t, equals 2 times y1. So this is, because y1 is e to the t, also 2e to the t, plus 0 times y2. So plus 0 times y2 here is e to the 2t. You can see that this is a true statement. So in fact, this is the relationship between the three functions that we have discovered. So because there is a relationship, because one of the functions is a linear combination of the other two, that's why these three functions are not independent functions. Okay, so that explains that first example. So now let's go through and talk about the second example. So in this second example, I'll teach you a nice little method for figuring out if functions are independent or not. So let's talk about t squared t and 1. So I'm going to let y1 be t squared, y2 be t, and y3 be 1. All right, so let's think about this here. So we want to figure out, let's pick on y1. So is y1 equal to some number times y2 plus some number times y3, right? If I can find those numbers, that would, kind of like what happened up here, that would tell me that y1 is a linear combination of y2 and y3. That would make these three functions not independent, right? Now, we're told that, they are independent. That's what we want to show. So we know that this is not going to be possible somehow. So because we know that this is not going to be possible, we might go down here and say, well, okay, maybe I'm being too generous, right? Maybe there's a third constant out here. In other words, maybe the constant in front of y1 is not 1. Maybe it's 7. Maybe that's why things didn't work out. Okay, so if I do that, let me reshuffle the names of things here so that the constants correspond to the indices, to the subscripts of the three functions. So if I do that, I'm really trying to find constants, k1, k2, k3, that make this equation true. Do they exist? Okay, so that's the same thing as k1, y1t minus k2, y2t minus k3, y3t equals 0, right? Are there constants that make this true? And then the next little jump that I'm going to make from here is I'm going to say, you know what? If these constants exist, right, I can just make this a positive sign, and it won't be k2. So let's call them now c's. So I'm going to say, if k1 exists, just relabel it c1. If k2 exists, call negative k2 positive c2. If k3 exists, call negative k3 c3. Okay. So again, I'm trying very hard to, if you've seen linear algebra before, I'm trying very hard to preview the condition for linear independence without having done that yet, because we will do that later on in the course. So here we are. We're trying to figure out, are there constants c1, c2, c3 that make this equation true? And specifically, we want non-zero constants, right? Just like what happened up here. There's a 1 in front here, there's a 2 there, and there's a 0. That's fine, as long as not all of them are 0. That will give us a relationship between the three functions, which makes it not independent. Great, so let's then convert what we have done down here to what it is. So I'm going to go a little further down and use the y1 and y2 and y3 functions themselves. Okay, so I'm going to use this three functions. I'm going to put them in here, and then that gives me this first equation right here. So c1t squared plus c2t plus c3 equals 0. Now you might be wondering, where do these other two equations come from? And this is the little method that I mentioned earlier I was going to teach you. So this equation has to be true for all t, right? It can't be that for some t it's true, for other t's it's not. We want to find the constants that make this equation true for all t. So given that, what I can do is take off my algebra hat, if you will, and put on my calculus hat, and I can differentiate this equation with respect to t. So I'm going to put a derivative out here, differentiate with respect to t. All right, so derivative of t squared gives me the 2t. The derivative of t just gives me 1, and the derivative of a constant is 0. So there's nothing here. Okay, so that's where this second equation comes from. I differentiated the first equation. And then I can do it again. Same thing with this equation. It should be true for all t. Take another derivative. The derivative of t is 1, so that leaves me with 2c. The derivative of c2 is a number, so that's 0. So I don't have anything left over. And that gives me this third equation here. And at this point, you can see, if I remove all this clutter, you can see what's going to happen. So this equation tells me that C1 is 0. I put it back here, that is gone, and this equation tells me that C2 is 0. I put C1 equals 0, C2 equals 0 here, and this equation tells me that C3 equals 0. Okay, so therefore, the only solution to C1 y1t plus C2 y2t plus C3 y3t equals 0 is all c's being 0. Okay? All right, that tells me that these three functions are independent functions. Right? Why does it tell me that? Because I literally cannot find a relationship that tells me one of these functions is a linear combination of the other two. Right? And I picked on y1 there, but I could have done the same exact thing. You know, y2 is a linear combination of these two, right? Moving those two terms over to the right-hand side. I can't find that, right? If such a relationship existed, let's say like y2 equals, y1 plus y3, then I could, move things over to the left-hand side, and I would have minus y3 plus y2 plus minus y1 equals 0. And in this form, that would tell me that C3 is negative 1, C2 is 1, and C1 is negative 1. Negative 1. In other words, I would have non-zero values for all three of the C's. But I have just shown that the only solution to this linear combination of the Y's is all three values of C being 0. Right? So that's why this shows me that y1, y2, and y3 have no linear relationships between each other. They're independent. There isn't one of them that can be expressed as a linear combination of the other two. Okay, so that's the method for determining independence of functions. And I will go back up here and erase this. So remove some of the clutter for the next video.